integrate x plus 2 over x cubed plus x dx using partial fractions. Let's start by getting the partial fractions expansion of the integrand. So we have x squared plus 2 over x cubed plus x. We can pull an x out of the bottom to get an x times x squared plus 1. And notice that this term right here is irreducible, so we're going to only have two terms. A 1 over x term, who contributes an a, and an x squared plus 1 term, who's going to contribute two letters in the form of bx plus c. Now we can stick this back on a common denominator and equate the numerators. So the a term needs the x squared plus 1. The bx plus c term needs the denominator of an x to be put on the common denominator. And so now these are equated, we can equate their numerators. And we'll have x plus 2, the numerator on the left, is equal to a times x squared plus 1 plus the quantity bx plus c times x, the numerator on the right. Now I just plug in test values. If we plug in the test value x equals 0, we're going to get 2 is equal to a times 1 plus 0. So a is equal to 2. And we can substitute that value right in here. We're out of good test values now, so we'll try some other ones. Say 1. If x is equal to 1, then we're going to get 3 is equal to a times 1 plus 1 plus b times 1 plus c, this whole expression, times 1. So if we clean that up, that's 3 is equal to 2a plus b plus c. We can substitute the value for a to get 3 is equal to 4 plus b plus c. And then if we solve that, we're going to get b plus c is equal to minus 1. Now we need another test value. So try minus 1. We're going to get minus 1 plus 2 is 1. That's going to equal a times 1 plus 1 again. Plus, we'll have a negative b plus c, all times negative 1. So if we clean this up, we have 1 is equal to 2a minus b minus c. Substitute what we know for a. We get 1 is equal to 4 plus b minus c. And then we can solve this expression. We'll have b minus c is equal to minus 3. So now we have two equations and the two unknowns b and c. Let's solve it with row reduction. First row would become 1, 1, minus 1. Second row is 1, minus 1, minus 3. We can leave the top row unchanged and subtract it from the bottom row to get 0, minus 2, minus 2. We could then scale that bottom row through by negative 1/2 to get a new bottom row of 0, 1, 1, and then subtract that bottom row from the top row to get, let's see, the bottom row is still 0, 1, 1, the top row becomes 1, 0, minus 2. And so what we've got here is the solution b equals negative 2 and c equals 1. We can substitute those values up here in the top, and we'll have completed the partial fractions expansion. 2x plus 1 for the numerator here. Now that we've got the partial fractions decomposition, we can integrate this. And remember, we're going to want to integrate this one integral for each coefficient. So we're going to have a 2 times the integral of 1 over x dx plus a negative 2 times the integral of x over x squared plus 1 dx plus a 1 times the integral of 1 over x squared plus 1 dx. One integral for each coefficient. Alrighty, let's prep this. So the integral of 2 times x to the minus 1 dx minus 2 times the integral of, bring the bottom up, x squared plus 1 to the minus 1 times x dx plus the integral of, bring the bottom up, x squared plus 1 to the minus 1 dx. This first integral is easy to attack. It's just logarithm. The second integral, the one in red right here, is going to require substitution. So let's do some scratch work. We're going to have the integral of x squared plus 1 to the minus 1 times x dx. If we try letting u be the expression in parentheses, x squared plus 1 to the minus 1, then we're going to go and have a 1/2 du is equal to x dx using the usual trick. So this integral becomes a 1/2 du for the differential, a u to the minus 1 for the integrand. If we integrate that, the 1/2 comes along for the ride, and we will get an ln of absolute value of u. And now we can substitute this in and back substitute. That's going to get us a 1/2 ln of the absolute value of x squared plus 1 for that red integral right there. Now we'll take care of that last piece. That last term is actually on the basic 20. That's just the derivative of the arctangent function. And so here we have one antiderivative. Let's cancel those 2's and clean it up. We have 2 times the natural logarithm of x minus ln of the absolute value of x squared plus 1 plus the arctangent of x. And we'll tack on a plus c, and we're done.